Now we solve this next question. Say you have alternator, further transformer, further some line. Say here transformer is given like this. And suppose a fault has occurred at this point F1. So what can be the nature of the fault there? Observe here, this fault is on the transmission line side of transformer, and how this secondary side of transformer is connected in solid neutral. So whatever the fault F1 is there, this fault must be involved with ground. This fault must be involved with ground. So observe this fault F1, it is on the line side of step-up transformer. So the secondary side of step-up transformer, how it is connected? Solid grounding. So fault F1 must be involved with ground. So what is that fault involved with ground most commonly occurring? It is a LG fault, double LG faults are the options. So the most commonly occurring fault involving the ground is LG fault. So the fault F1, it refers to what? LG fault. So F1 refers to what? LG fault. Now say a fault F2 has occurred here. Now where the fault F2 has occurred? On the alternator side of this step-up transformer. And how the primary of the step-up transformer is connected? Connected in delta. Delta means no ground. So this fault F2 is not involved with ground. This fault F2 is not involved with ground. If this fault is not involved with ground, what about that particular fault now? You can mention double L fault or triple L fault. By default in the questions they refer to unsymmetrical faults only. So the answer for this is double L fault. What is the answer you get there? You mention that as double L faults. And say fault has occurred at the terminals of a synchronous generator. Fault has occurred at the terminals of synchronous generator. Then which fault current is severe? LG fault current is severe. So now we analyze this next one. Of course, this is asked in one of the GATE question papers. Now where the fault is? On the terminals of a synchronous generator. And how the synchronous generator is protected if not mentioned? Solid grounding. So the fault F3 must be involved with ground here. Fault F3 must be involved with ground. So for a fault on the terminals of synchronous generator, for a fault on the terminals of synchronous generator. Which is the severe fault? LG fault is the severe fault here. So here we say it is the fault involved with ground. So which option we mention? LG fault, double LG fault. We prefer the most commonly occurring fault. So the answer is LG fault here. So what is the answer you get? It is LG fault. Solve this. This is one of the question paper. When the sequence of fault, so faults may occur on a transmission line are given here 1, 2, 3, 4. It is 3-phase LLG, LLLG. So now we have to find out the decreasing order of severity of faults. The decreasing order of the severity of faults. So where you will have less reactance, there you say the fault is high. So you calculate IR1 equations for all the faults. It is easy. 3-phase, what you have? 1 by X1 equivalent per unit. LLG 1 by X1 equivalent plus parallel combination of X2 and X0. LL 1 by X1 plus X2. What about LG? Sum of all the three. So where the reactance is less? For 3-phase fault. Further less for LLG fault. Further less for LL fault. Further it is less for LG fault. So the decreasing order of severity of faults is 1, 2, 3, 4. That is the decreasing order of the severity of faults here. Now we solve this next question. These asked in one of the GATE question papers. The sequence components of fault current are as follows. What about positive? J 1.5 per unit, negative minus J 0.5 per unit, 0 minus J1 per unit. The type of fault in the system is so we have to identify what is the type of fault in the system. We have to evaluate one by one. Can it be LG fault? You know, in LG fault, IR1 equal to IR2 equal to IR0. So it is not LG fault. Can it be LL fault? In LL fault, IR0 0. So it is not LL fault. Can it be triple L fault? In triple L fault, IR0 0, IR2 0. So it is not triple L fault. Can it be LLG fault? In LLG fault, IR 0. IR 0 means the sum of all the sequence currents are zeros. So IR1 plus IR2 plus IR0 0. So which fault it refers to now? LLG fault. Refers to which fault? LLG fault. Now we solve this next one. This is from the IES question paper. A fault occurring at the terminals of an unloaded synchronous generator operating at its rated voltage has resulted in IA0 is J 2.37 minus J 3.05, IA2 J 0.68 per unit, VA0, VA1, VA2 0.237 per unit. The fault that has occurred is. So what is the nature of the fault now that has occurred? Similar to the last one, IA 0, so IA1 plus IA2 plus IA0 0. So it is LLG fault. So fault that has occurred is a LLG fault. Now to solve this next question, the zero sequence current of a generator for LG fault is J 2.4 per unit. The current through neutral during the fault is. So what will be that neutral current in LG fault? We have derived 3 IR naught per unit. So 3 into J 2.4, how much you get? 7.2 per unit. So this is the current flowing through the neutral during fault. How much you get? J 7.2 per unit. So this is how you calculate and find what is the neutral current here. So formula is simple, 3 IR naught per unit. And now we solve this next question. The single line ground fault current in fault phase is 300 amperes. The zero sequence current is. Now you know in the case of LG fault, how to analyze in case of LG fault? Fault current IF per unit equal to 3 IR naught, but here given in amperes. So IF in amperes how much? Either in per unit or amperes, same formula. Fault current is 300 amperes. So what is this zero sequence current now equal to? 100 amperes. So how much IR naught is now equal to? 100 amperes here. So on simplifying, you get that answer as 100 amperes. Now we solve this next question. This from one of the IAS question papers. For alternators each rated at 5 MVA, 11 kV and 20% reactance are working in the parallel. Now for this we have to find out the short circuit level at bus bars. The short circuit levels at the bus bars. So how to calculate this now? So 4 alternators are in parallel. So what will be the equivalent reactance? 4 in parallel, you get 5%. Then how you find what is the short circuit MVA? You have derived. It is base MVA by percentage X into 100. In the yesterday's session on per unit formula, you have written this way. So base is 5 MVA, 100 by 5. So how much you get the short circuit MVA? 100 MVA. Base MVA or rated MVA, 5 MVA only. But short circuit MVA you check, it is 100 MVA. You get that answer as how much? 100 MVA. Now we solve this next question. And this is also from the IS question paper. And here also 4 alternators only. For identical alternators, each rated 20 MVA, 11 kV, having a subtransient reactance of 16% are working in parallel. So the short circuit levels at the bus bars is. Similarly, you calculate. So 16%, 4 are in parallel, you get 4%. So what is the short circuit MVA? 100 by percentage X into base MVA. So 100 by 4, base is 20. So how much you will get now? 500 MVA. So base MVA or rated MVA 20 MVA only. But what about the short circuit MVA? Short circuit MVA is 500 MVA. Observe that is the value you get here. Now we solve this next question. a system having 4 alternators each rated at 11 kV, 100 MVA and having subtransient reactance .2 per unit is shown in the figure. If fault on one of the feeders occurs near the bus, so what is the fault level for x equal to 0? So in the question you are given this figure here. And fault is at this point. So this is the reactance X here. Now when that X is equal to 0, you should find now what is the fault level. When that value of X is 0, you should find what is the fault level. So when you draw the reactance diagram for this one, so reactance X equal to 0. Each subtransient how much now? 0.2 per unit. Each one is 0.2 per unit. Fault has occurred here. So you find what is X equivalent per unit. How that X equivalent per unit will be? 4 reactances in parallel, each of 0.2. So how much you will get? 0.05 per unit. So what is the short circuit MVA? It is base MVA by X equivalent per unit. What is base MVA? 100. Equivalent is 0.05. So you have to simplify this one and find out what is the answer here. You get it as 2000 MVA. So answer for this question is 2000 MVA. Now we solve this next one. This from an IS question paper. Two power stations, S1 and S2, are interconnected So here it is given that it is a three-phase symmetrical short circuit which has occurred at the middle of the transmission line. That is given in the question also. It is the point F. And further it is asked to calculate what is the change in the equivalent fault reactance with one of the generators of S2 disconnected here. So in the figure you are given this one. And at the middle of the line, the fault point is denoted like this, at the middle of the line. Now observe what is the equivalent reactance to the left side, 0.4. What about to the right side now? So the equivalent reactance, first one is before fault, you represent by naught, and next is during fault, you represent by 1. Now before fault, left side 0.2, 0.2 in series. What about right side? These 0.4s which are in parallel added to that 0.2, and this total is in parallel with this one. How much you get on simplifying? 0.2 per unit. What about X1 equivalent 1? Now one of the generators of S2 is disconnected. Now with one of the generators of S2 disconnected, what will you get now? 0.2 and 0.2 left hand side, they are in series. What happens to the right side? 0.4 and 0.2 are in series. So 0.4, 0.6, how much you get? 0.24 per unit. So now we have to find out what is the percentage change in the reactance. How to write? After fault, during fault minus 0 fault, that is existing initially, divided by 0 fault. So minus 2.24 divided by this value. So how much you get that percentage reactance? You get that percentage reactance equal to 20% here. So this is how you calculate and find out what is the percentage reactance. So always in the denominator you write whatever the value is there before fault. Before fault how much? 0.2 per unit. So mention the value before fault. Now you have 5 minutes break. First question is by Sanju. In question number 26, you have not mentioned the star connection to generator. How did you decide the fault considering just the transformer connection? See, in none of the questions you will be given the connections of generator. For our analysis, you consider that generator is solid grounded. And based on that you analyze. And only you are given the transformer primary connection, secondary connection. Check which side the fault has occurred. Check how the connection is particular to the winding on that side of the fault. Accordingly, you decide and find and conclude what is the fault. Next question is by Vishwam from Agartala. Is three-phase and triple L fault same? Yes, they are same. Next question is by Somdev from West Bengal. In question 25, why we have considered LG fault instead of LLG fault? Because LG fault is the most commonly occurring fault. So preference is for the most commonly occurring fault, LG fault. In question 26, according to the diagram, how we identify whether it is LL or triple L like that? Now always it is unsymmetrical faults occurring mostly in common. So refer the answer as LL fault. Now we continue with our next questions. So this is from one of the GATE question papers. A LG fault occurs on an unloaded generator in phase A. Positive, negative and zero sequence impedances are J.25, J.25, J.15 per unit. So you have that generator neutral is grounded. Through a reactance of J.05 per unit. Next it is mentioned the pre-fault generator terminal voltage is 1 per unit. Now we have to find out what is the fault current. You can observe here we have LG fault. In case of LG fault, what is the magnitude, what is formula to find the fault current? 3 times ER1 by X1 equivalent plus X2 equivalent plus X0 equivalent. What is the pre-fault voltage? 1 per unit. x1 equivalent and j.25, x2 equivalent j.25, x0 equivalent is xr0 plus 3 into xn. You know the basic formula of x0 equivalent. How you write the basic formula? It is xr0 plus 3xn. So on simplifying, this is the answer you get. So how much you get? Minus j 3.75 per unit. Minus j 3.75 per unit. Now we solve this next one. This is also from a GATE question paper. A 500 MVA, 50 Hertz, 3-phase turbo generator produces power at 22 kV. Generator is star connected and its neutral is solidly grounded. Their sequence reactances are x1, x2 is 0.15, x0 0.05 per unit. Further it is mentioned, it is operating at rated voltage and disconnected from rest of the system. That is, you say it as no load. The magnitude of subtransient current for LG fault at the generator terminals in the per unit is. So we have to calculate what is the magnitude of subtransient current. Subtransient means XD double dash. XD double dash, we have the corresponding fault current. So what is the fault current for LG fault? 3 ER1 by X1 equivalent plus X2 equivalent plus X0 equivalent. On simplifying this one, here it is 0.15, XR0 0.05, and what about the reactance? Solidly grounded, so Xn is 0. So on simplifying this one, you get the answer 8.55 per unit. So on simplifying this one, you get the answer as 8.55 per unit here. Now we solve this next question. The neutral of a three-phase 15 MVA, 11 kV alternator is solidly grounded. The positive, negative and zero sequence impedances are J1.5, J0.8 and J3 ohms, 0.3 ohms respectively. A line to ground fault occurs on the phase A. Now for this we have to calculate the magnitude of fault current now. So now further we have to calculate what is the magnitude of fault current. So how you calculate the magnitude of fault current now? Fault current in amperes, because everything is in ohms and relations. Further 3 ER1 expressed in volts and total denominator X1 equivalent, X2 equivalent in ohms, X0 equivalent in ohms. And what is the ER1 value? You know, ER1 per unit or ER1 in volts equal to ER in volts. So what will be ER? The rating of alternator is selected as ER. So 3 into 11 kV. What about X1 equivalent? 1.5. What about X2 equivalent? 0.8. What about X0 equivalent? J0.3 and plus 3xn. Xn how much? 0. Because it is solidly grounded here. We have that as solidly grounded. So how much you get? 33 by how much J? 2.6 here. 33 by 2.6. You will get 12.7 kilo amperes. So answer is 12.7 kilo amperes. So this is how you calculate and find out what is the fault current here. Now we solve this next one. It is also based on the LG fault which you did at the beginning. A 100 MVA 20 kV generator has XD double dash or X1 or X2 how much? 20% and X0 equal to 5%. So now we say that is neutral is grounded through a reactance of 0.32 ohms. So the generator is operating at rated voltage at no load and is disconnected from the system when a single line to ground fault occurs at its terminals. The subtransient current in the fault phase is. So how you find out this subtransient current? It is fault current. Here also you require in amperes. What is the formula? 3ER1 measured in volts divided by sum of all the reactances, X1 equivalent, X2 equivalent plus X0 equivalent. How much it is given as 20 kV. 3 reactances are given 0.2, 0.2, here 0.05. What about the reactance 0.32? 3 into 0.32 here. So 3 into 20 into 10 cube divided by how much you get? 1.41. So this is what we have to calculate here and find out what is the answer here. So here it is given as 0.08 place. So these values are in per units here. So express the calculation in per unit here. You get the fault current in per unit first. 20%, all these are the per unit reactances here. Now how to calculate using this data now? You can verify the question. The 20% and the 5% are the percentage reactances. And how to get those percentage reactances? 100 into per unit reactance. You mention as 100 into per unit reactance. So now the neutral reactance is given 0.32 ohms. So now you find out what is the neutral reactance in per unit. So Xn in ohms multiplied with base MVA by kV square. So using this formula you calculate first. How much 0.32? How much base MVA? 100 MVA. Base kV 20 square. How much you get? 0.08 per unit. And now you substitute this value here. Pre-fault terminal voltage is 1 per unit by default, because alternator rating itself is base value. So per unit, how much? The rating by base, you get it as 1 per unit. So it is 1 per unit. How much here? 0.2. Here also 0.2. X0 is 0.05 plus 3 into 0.08. So on simplifying this one, you get the answer 4.34 per unit. So this is the fault current in per unit and Xn per unit. So how to find the subtransient current in fault phase in amperes? In amperes we have to calculate now. So fault current in amperes, you know the formula. Fault current in per unit, base volt ampere divided by √3 times base voltage. What is fault current in per unit? 4.34. Base volt ampere is 100. And other is 20 kV. So this is what we have to calculate. You get the answer as 12.55 kiloamperes. So important part of this calculation is, these are the reactances given in percentage. So write them as per unit reactances. So first to convert that 0.32 ohms neutral reactance into per unit neutral reactance, substitute here, you get fault current in per unit, then verify, you get the fault current in amperes. So further you get the fault current in amperes. Now we solve this next question. A single line to ground fault occurs on an unloaded generator in phase A. Positive, negative and zero sequence reactances of generator are given in the question: 0.25, 0.25, 0.15 per units here. Further it is given that the generator neutral is grounded through a reactance of 0.05 per unit. The pre-fault generator terminal voltage is 1 per unit. So here we have to calculate the positive sequence subtransient current in per unit. So we have to calculate here the positive sequence subtransient current. So all the previous 5 questions you have calculated subtransient reactance means IF per unit. Positive sequence means we have to find out IR1 per unit. Here it is given as phase A. So IA1 per unit. So what is the formula we write? ER1 by not 3ER1, only ER1. X1 equivalent plus X2 equivalent plus X0 equivalent. So we substitute the values now. It is by default 1 per unit. X1 is 0.25, X2 0.25, X0 0.15 plus 3xn. So we have to calculate this one and find out the answer. You get 1.25 per unit. So the answer for this question is 1.25 per unit here. Now we solve this next question. This is asked in one of the GATE question papers. Regarding the LG fault. A 20 MVA 6.6 kV 3-phase alternator is connected to a 3-phase transmission line. The per unit positive, negative and zero sequence impedance of alternator are J.1, J.1, J.04. Neutral of alternator is connected to ground through an inductive reactance of J.05 per unit. How much it is given? J.05 per unit. Now further it is given the per unit positive, negative and zero sequence impedances of transmission line are J.1, 0.1, 0.3. Further it is given all the per unit values are based on machine ratings. Next we have a solid LG fault occurs at one phase of the far end of transmission line. The voltage of alternator neutral with respect to ground during fault is. So this is what we have to calculate here. If you check the question, you are having two power system components here. What is the first one? We have alternator. Alternator data is given, further line data is given. So first we have an alternator followed by transmission line. And where the fault has occurred at far end of transmission line. Say fault has occurred here. Then how you calculate what is the voltage of alternator neutral with respect to ground? First to calculate what is the fault current in per unit. So how to calculate the fault current in per unit LG fault? It is 3 ER1 by X1 plus X2 plus X0. So how much ER1 value is 1. Now X1 equivalent means you should include the positive sequence reactance of alternator and line. So how much for alternator? J.1. How much for line? Again J.1. Now negative sequence reactance of alternator J.1, line is J.1. Negative sequence reactance of alternator, line completed. Now zero sequence reactance of alternator, how to write? It is J.4 plus 3xn. How much it is? 0.05. This totally for alternator. Now for line J.3. So verify the power system network. We have both alternator and line. So it is like a series combination. So everywhere you include their reactances in series. So on verifying this one, you get minus J 3.37 per unit. Now how to write what is the voltage to neutral in per unit? It is IN per unit, XN per unit. And while doing the LG fault, LLG fault, we have written for faults involved with ground, IN per unit is equal to IF per unit. For faults involved with ground, IN per unit equal to IF per unit. So how much IN? Same as IF. And we substitute now 3.37. XN is 0.05. How much? 0.168 per unit. Now how to convert this per unit to volts now? So Vn per unit multiplied with the base voltage in volts. How much Vn per unit? 0.168. Base voltage how much? The rating of alternators is considered as base values. So why you consider alternator rating as base value? Because you know alternator is the first component in power system network. So the alternator ratings are considered as base values. How much the base value now? 6.6 kV. And why you divide with √3 now? You measure the voltage to neutral between which points? Ground and neutral. So between ground and neutral, always what you represent? You represent the phase voltage. Between ground and neutral, always you represent the phase voltage. So on simplifying this one, you get the answer 642.2 volts. So on simplifying, you get the answer as 642.2 volts. So once again you practice all these questions based on LG fault analysis. So after the lunch break we continue with the numericals on other types of unsymmetrical faults and symmetrical faults.